So I want to talk about rationality and how much of that might be found in language models. And in particular, it's the theme of the workshop, I want to tie to questions about benchmarking. Let me just start from scratch. But what the issue is when we talk about rationality. So rationality, the term is used in a number of different ways. And there is one that I feel like is a little bit more prominent in computer science and one that's more prominent in philosophy. Now, on the computer science way of thinking about rationality is that like an AI is rational on a sort of thin minimalist notion, just in case it does what it's supposed to do. It does the right thing, it's doing it properly, it's working properly, it's irrational. So on this sense, benchmarking rationality obviously just comes down to, does the thing do what it's supposed to do? And that's not really, it's interesting in cases, but that's not really the substantial notion that we want to focus on. Instead, I want to look at more like a philosophical notion of rationality, where generally when we evaluate some person for rationality, we wonder about the quality of their particular specific states or the quality of their action. So do these people that are rational, do they act properly? Do they have the right kind of beliefs? Are the beliefs overall or the internal mental states properly, favorably evaluated in a certain way? So I want to go over some details of different aspects of rationality in just a little bit. First, let's talk about the issue about why this might be significant. So the question whether or not AIs, and in particular language models, are rational in this sort of more philosophical sense, where we evaluate internal representational states like beliefs, like intentions, agency, and so on and so forth. That's a substantive question that's often a little bit overlooked, that people just assume that they would be if they're really good, if they're super intelligent and things like that. So an example of this is this argument for the instrumental conversion thesis in the debate about alignment and AI safety and things like that. So the thought simply is that if an AI has a particular goal, then it will be means ends rational and adopt the derivative goals, the ones that are necessary to acquire its ultimate goal, achieve its ultimate goal. So, for example, if its goal might be whatever, predict the weather or the stock market, it will also then derivatively acquire the goal of ensure its own self-preservation, allocate resources, and so on and so forth. And the argument for that is that, well, it would be means ends rational. It would be very intelligent, super intelligent, possibly. So the norms of rationality require it to adopt further goals. But it's not completely clear whether or not this even makes sense, or the assumption that anything like rationality is properly applicable to a system like this is slightly overlooked. So I want to look at this in some more detail in this talk, and in particular, tie it to questions about benchmarking. And so this will be related to what I guess all earlier speakers Anani called the deep versus shallow benchmarking. And I wasn't unfamiliar with that terminology, if that's standard terminology. I use like internal versus external benchmarking. But the thought is that to assess questions of rationality, what do we look at? What do we benchmarking? Are we benchmarking the output, the performance, the capabilities of the model, just looking at what they're doing on the outside? Or do we need to look on the inside and seeing what's going on inside to properly assess the questions of rationality? And so it seems natural to think that you have to look on the inside just because the proper subject, the objects of rational evaluation are, in the traditional case, internal representational states like beliefs and desires. There's a question about how those relate to, like features of the performance or the outside, the external aspect of the models. But the target will be, are these models rational? Does the case of rationality properly apply? All right, so that's the overall topic. So I want to look at a couple of things in more detail. But first, let's look at a heavily neglected topic of benchmarking, a special case that there's very little literature on, and I think that needs to change immediately. I mean, that is benchmarking politeness among trees. So consider the following arrangement, the following forest here. I don't know if you can see it. Look how incredibly polite these trees are. They're spaced apart. They leave plenty of room for people to go through. The ground is pretty evenly. The branches are all very high. They don't interfere with anybody. Extremely polite. But contrast this with these rude trees over here, which cover the whole area. They're blocking everybody. They're too close together. They're disorderly. And highly rude arrangement of trees versus the other one is more polite. So this one, we could obviously measure and evaluate politeness among trees. So we could come up with a benchmark that measures politeness. So you could write a paper that we introduced the PAT benchmark, politeness among tree benchmark, that has various different aspects that assign scores and evaluations of particular forests. We could have a leaderboard for politeness. We could point out that the PAT benchmark is inadequate because it completely neglects considerations of the canopy, and it completely neglects considerations of the root placement and how likely it was somebody would be tripping over this. So we can extend it to introduce another benchmark, the extended PAT benchmark, XPAT benchmark, which goes further, and so on and so forth. Somebody could try to plant a forest specifically to have the highest score on the XPAT benchmark, where we get the best result overall by carefully curating the trees. We could have all kinds of tests, including like, what if you trim the branches? Will they grow back? That yes, they're rudely in the way, then that would count against, and so on and so forth. Okay, so obviously something is going wrong here, right? So what we're doing here when we're benchmarking politeness among trees is we're not really benchmarking a feature of the trees themselves, right? The trees are not polite or impolite. The trees are just there. We might have a reaction of politeness or impoliteness, and ultimately the score of the benchmark is tied to our reaction. So the true ultimate subject of the benchmarking is really us, not the trees. Okay. So this analogy, I think, will also apply to considerations about rationality. So what is it that we are benchmarking when we're benchmarking rationality? Is it ultimately about us and our reaction, or ultimately about the models that produce the various things? Okay, so let's make a first important distinction, namely the one between a system being arational, which just means that the norms of rationality do not apply to it at all. So, this water bottle is irrational. It makes no sense to apply requirements of rationality to it. That should be countered with being irrational, where the thought is that, norms of rationality apply to you, but you don't live up to the norms that apply. So an irrational person is somebody, who has contradictory beliefs or gambles in Macau or loses, let's say, but they're not very good at it. And so on and so forth. With rational, somebody's rational just in case that the norms apply to them and they do live up to those norms sufficiently substantially. So trees are apolite, not impolite. Trees, the norms of politeness do not apply to trees at all. It's not that they violate the norms that apply to them. They are apolite, not impolite. And people can be polite. All right. So the question is, whether or not language models in particular are irrational, irrational, or rational. So do the norms apply to them? If yes, do they live up to the norms that apply to them? Okay, so the first step to look at is whether or not the models would have any suitable internal states that are properly subject to rational evaluation. So paradigmatically, these are states like beliefs, and but also other states of a similar kind. So it could be like an intention, desires, and so on and so forth, agency. All these states are generally considered subject for rational evaluation. If none of these states would apply to the models, then it would be reasonable to say that they are irrational. The considerations of rationality are misplaced because they don't have the suitable states that would support rational evaluation. This will be our first step. So, okay, so let's think about different aspects of rationality. Rationality is a whole complicated set of evaluations of these particular states. And some of them are really substantial and difficult. But generally, the ones that get the most attention are maybe the ones that are also the most difficult, like say, for example, reasoning. So reasoning is a rational activity. It's subject to rational evaluation. And it's, of course, there's a great interest in reasoning for language models, but it's not really the simplest case to consider. So let's first start with something like coherence. So coherence norms are norms of rationality that concern how the internal states of a system are coherent with. So in the simplest case, a coherence norm concerns not having contradictory beliefs. So not to believe, that I don't know, dim sum is delicious and also dim sum is not delicious. So these two beliefs do not cohere with each other. A norm of rationality, arguably, right, requires you not to have a contradictory beliefs like this. So coherence norms generally are synchronic norms, so they apply to a system at a time. They do not necessarily apply to a system over time. But norms of rationality can also apply to a system over time. So, for example, inference is usually a temporally extended process. Reasoning, temporally extended process. Responding to evidence, temporally extended process. And responsiveness to reasons. These are all things where norms of rationality apply that concern internal representational states. And they could be across time or at a particular time. Okay, so I want to suggest that whether or not language models are rational, these rational norms apply to them is not at all obvious and clear, and it's a slightly tricky case. And I want to focus simply on the simplest case here, namely coherence norms. Okay, so this will be my focus. I'll talk maybe a little bit about diachronic belief revision, but so let's first just ignore all the complicated stuff and look just at simple norms of coherence. All right, so coherence norms, in turn, there's really two main types that I want to focus on. So the first one is basically what we could call logical coherence. That's like the belief P and also belief not P. You don't want to believe something and its opposite at the same time. You're incoherent. The second version is a probabilistic coherence. So this is what in philosophy is often called credences, like the strength of belief. You assign probabilities to how strongly you believe something. And then there are some norms of coherence about how these credences should relate to each other. So for example, if I believe that it's going to rain reasonably strongly, let's say 80%, then I should believe that it's not going to rain reasonably weakly, ideally 20%. So that either it's going to rain or not rain should add up to 1. So this is a kind of a coherence that concerns the strength of belief. It's not necessarily coherence about beliefs about probability. So that needs to be distinguished. So there's one thing about believing that it's going to rain with a chance of 80% and believing that it's going to rain with a chance of 20%. Those two are not contradictory, or even, let's say, one is 30%. These are not contradictory beliefs necessarily. There's some incoherence there, but it's not the same as the focus by focusing on the coherence of credences. Strengths of belief should be properly adjusted, arguably, right? So that's another norm of coherence. So another synchronic coherence norm concerns other sort of different kinds of states. So for example, if there's a number of different kinds they don't just apply to beliefs, but rather the combination of certain things. So for example, if I believe that the best thing overall to do is A, but I intend to do B, right, then there's some incoherence in my mind. There's something incoherent there, some tension. This is, again, an advanced topic that I don't want to touch on. We're just focusing on the simplest case, logical and probabilistic coherence, and whether or not language models are under rational requirements of this particular kind. Okay, so let's look at the first one first, namely just logical coherence and whether or not the models are under logical coherence norms. And the question here is closely tied to whether or not there is anything like a belief. A belief is an internal representational state that represents the world being a certain way. And if models do not have representational states of that kind, they do not have beliefs. And if they do not have beliefs, then logical coherence norms do not apply to them. So the first question to answer is, do these models have internal representational states? And there's a lot of debate about this. And I want to just simply grant that. I want to say that, yeah, let's assume that internal states of the model somehow or other represent the world as being a certain way. Okay. The question still remains whether or not any of these internal representational states are beliefs. And that is a further requirement than simply having an internal representational state. Because there's lots of different ways to represent the world. Believing something is just one of them. So let's grant this one and look instead at a different argument that none of the internal representational states are beliefs. And that argument simply goes as follows. So language models are machine learning models. Right? They are trained on data and they're supposed to learn the data. But now in light of this, you think that the states of correctness, the standards of correctness for the internal states of the model are the ones that properly contribute to what the model is supposed to do, model the data on which it was trained. Right? So so if you look at the internal states, when is an internal state of a model defective? When is it not doing what it's supposed to do? Well, here's one straightforward way. It doesn't properly contribute to what the model in general is supposed to do, namely learn the data. If that's so, then that state is defective. Okay, and those are the standards of correctness of the internal states of machine learning models. They have a particular contribution to make to the overall purpose of the model, namely to learn the data. Okay, but so now the argument is that belief states who have further requirements on the standard of correctness. So when a belief state is defective, is not includes another extra dimension. So this is a familiar thought in philosophy that your belief aims at the truth. So here's the thought simply by thinking about a particular belief I might have. So suppose I believe that I am the head chef at a fancy Cantonese restaurant. Now that belief is defective simply because it is false, even when it has other positive upshots or benefits. So for example, it might give me great confidence in the kitchen to believe that I'm a head chef in a fancy restaurant. But nonetheless, even if it has positive downstream consequences, that state is defective simply because it is false. And so this is a special thing about belief states, that they have this condition that they are defective simply because they're false. It doesn't apply to other representational states. So for example, if I imagine that I'm the head chef at a fancy Cantonese restaurant, then simply because that's false does thereby not make that imagining defective. Imagining does not have the same constraint of the same standard of correctness as belief, namely to be true. If it's not true, it's defective. Okay, but so now putting those two together, it looks like that the internal states of machine learning models are not belief states because they have different standards of correctness. Their standard of correctness is simply exhausted by contributing to what the purpose of the model is, namely to learn the data. And to learn the data doesn't require that the internal states are true. It just requires that they properly contribute to what machine learning is supposed to do. Okay, so this is the first straightforward argument against belief states being states of machine learning models that grants that they might have representational states, but says that none of the representational states can be beliefs. Okay, but this argument is not quite conclusive. And the idea is simply that we need to distinguish the pre-trained models from the fine-tuned models. So the pre-trained models, I just mean that that's a model that's simply trained on text. Just looks like here's a bunch of text, learn the patterns of that text, and then maybe you use to predict what the next word will be or something like that. But it's simply a model that's trained solely on text. And of course, the models that we interact with are not like that. They are pre-trained and then further fine-tuned. First for, let's say for question answer format, and then furthermore, they're fine-tuned with reinforcement learning from human feedback for giving good answers. And the goodness of the answers is evaluated along different dimensions, being helpful, being not offensive, and also being truthful. So being truthful is one of the criteria for which the models are fine-tuned after their pre-training. And so now, if you bring that in, the thought is that maybe that can bring in the standard of correctness of internal states to being truthful, because if now the criteria on which the model is trained is to be truthful in the fine-tuning process, then that might bring in this particular goal. It might give the internal states the status of a belief. But I think it's not completely clear if this is actually good enough. There's a number of different reasons for thinking about this. So one of them is one that I will come back later, is that in the pre-training, the models are trained on incoherent text. So incoherent text just means that the text on which they're trained itself contains contradictory statements. So there's a statement that says, dim sum is delicious, and then there's a one that says dim sum is not delicious. Part of the training is supposed to pick up the patterns of those words. So if you think that the belief somehow, the content of the belief must come from what the model was trained on, then there is some slight tension here between, on the one hand, being trained on incoherent text, on the other hand, being fine-tuned for truthfulness. And it's not completely clear how those two get together. So I will talk about this a little bit more just a little bit later. But in any case, so belief is on the table by thinking about simply about the internal states, there being representational states, and they having the standard of correctness of being truthful that is given to these states via the fine-tuning process, but not through the pre-training. Suppose that's also. Oh yeah, and I should point out that that this is all done, by looking at the internal stuff. So it's not that you just look at the output of the model, ignore what's inside, and have some general argument that anything with an output like this must have beliefs because of, say, Dennett or Davidson or other, like shallow benchmarking kind of considerations where you just focus on the outside. But this is not supposed to be like this. It's supposed to be, let's look at the inside. Let's see what kind of states are inside. Are they representational? Are they the right kinds of representational states? And if the answer is yes to all those, then belief is on the table. And if belief is on the table with the aim of truthfulness, then arguably the rational requirement of logical coherence is derivative on it. And the argument for that is simply that contradictions are not true. They cannot be true. So if your goal is to represent the world truly, then if you represent the world in a contradictory way, you're not doing what you're supposed to do. And so there's a requirement coming from the goal of being truthful that you ought not to have contradictory beliefs. And so the rational norm of logical coherence can be seen as being applicable derivatively on the process of fine-tuning the model for truthfulness. With these caveats in mind about the possible, tension in these requirements about, on the one hand, the pre-trained model being trained on inconsistent text, and on the other hand, being fine-tuned for truthfulness. Okay, so that's the first issue. So it's not completely clear if this is legitimate, if we have beliefs and if we have the rational applicability of the logical coherence norm, but it's on the table. It's straightforwardly on the table if we're granting that there are representational states at all. Okay, but so let's think about the next issue of, namely, credences. Can we make sense of strength of belief? And can we make sense of the rational requirements to coherent credences being applicable to language models? Okay, so the issue is this. Now, how would you make sense of the strength of a belief of a model? So the model might have certain outputs. It might produce certain text, let's say, and you might think that that could be indicative of what it believes. But how do you make sense that it believes it very strongly or it believes it only weakly? You want to assign probabilities to basically propositions that correspond to the strength of belief in a systematic way. You want to say that for any proposition, here is a probability that the model that somehow comes from the internal states of the model that corresponds to the strength of belief of that proposition that is appropriate for that problem. Now the thing is that you want to do this in a systematic way, and the models they have all kinds of probabilities built into them, so they're very probabilistic. You want to exploit the probabilities that are inside the models that are being used to assign this sort of coherent credence function, and then evaluate whether or not the assignment of credences that's done in this particular way meets the rational requirements. And so the problem is the probabilities that are assigned in the models, they concern, let's say in this simple case, like let's say then the probability of the next token being a particular token. So, if the text starts a certain way, then there's a probability assigned to what be the next token, aka next word that comes after this assignment. But that doesn't really give you any probabilistic assignment of strengths of belief to propositions. It applies to token level things. You need to have probabilities that are assigned to propositions who have a coherent credence function that applies to propositions. Okay, so the straightforward idea to make that transition is minimal assent connection. You consider how strongly will the model predict that the answer is affirmative if you ask it the question whether or not a certain proposition is true. So in the simplest case, you just do this. You say that the proposition, the credence for a particular proposition P corresponds to the probability that the model will say the next token is yes, if prompted with the question, is it the case that P? Okay. So that's a straightforward association of probabilities assigned to propositions that comes from probabilities assigned to tokens. You can use the probabilities. So this big P is just the language model probabilities. You can use the probabilities that are assigned in the model to tokens given particular initial sequences, and then convert that into the strengths of belief. Okay, but this is not quite working. Okay, so there's a couple of things that are wrong with it. So the first one is that that sort of undercounts, because the model might not just say yes or no. The model might say yes or sure, or I'm not allowed to answer, or there's a number of other things it could output that then the probability of yes might be only 10%, but intuitively it has a much stronger credence in that, because there's a number of other ways it could also assent to something. So the next thing to try is you just you consider what an assent sequence would be. So a sequence of tokens that would correspond to assenting to something. So you say basically, yeah, yes counts, that's an assent sequence, and sure counts, and I totally believe that counts, and so on and so forth. And then you take the probabilities that the model will produce one of these assent sequences. And after being prompted with the question whether or not that be. Okay, so since these probabilities are like a probability distribution, you can just add those up, and that gives you a coherent assignment of an assent probability to a proposition that P. Okay, but this also does not quite correspond to credence yet, because for the reasons I just mentioned, right? So the model might refuse to answer the question for a number of different reasons. It might say, as an AI language model, I cannot comment on any controversial topics, and so on and so forth. And that would then take away from some of the probabilities that should really be assigned to the credence, because it might, in some sense, believe it, but just not being allowed to say it, something like that. Okay. So the next better way to do it is just to think about what's the ratio of assent versus dissent probabilities. Okay, so you say that instead of just having assent sequences, you have dissent sequences, which could include like no, no way, etc. Whatever it is that you have to specify by hand, and then you assign to each proposition both the assent probability and the dissent probability, and then you basically normalize and say that the credence of P is the assent probability divided by the assent plus this in probability. And so now you're sort of factoring out all the, I'm not allowed to talk about it. Any other ways that the model might respond to the question do not correspond to an ascent or descent. Okay, so it's a start, so the idea is that you can make sense of credences. This way is not the final word, I think, but it's a solid start. So the question then is, can we make sense of rational coherence norms that correspond to credences, like the ones that we've been talking about just now? So okay, so let's so probabilism. This is like terminology within philosophy. Like probabilism is the view that credences ought to satisfy the axioms of probability theory. So that means, in particular, if the credence in P is particularly 80%, then the credence in not P should be 20%. So those credences should add up to 1, and they should all be between 0 and 1, and so on and so forth. So the question is it correct that the model is under the rational norm to have probabilistically coherent credences? So far, we just assigned some probabilities to these models, to propositions based on next token probabilities that come from sort of the internals of the language model. Can we also make the case that the rational requirement of probabilism applies to the model? And here you can use sort of like off-the-shelf philosophical arguments, namely the so-called accuracy arguments for probabilism. So the accuracy argument for probabilism says, this is, I guess, goes back to Jim Joyce, who first, correct me if I'm wrong, who first proposed these. And the thought is simply this, that if you have some sort of measure of how accurate your credences are. So the thought here is that, let's say, if you believe it's raining 80% and it's actually raining, then, you're 20% off. You're a slight distance off. If you're believing that it's raining 90%, you're closer. So there's a sense of accuracy that the higher your probabilities are for things, your credences for things that are true, the closer you are to the truth. So if your goal is being truthful and accurate, right, then you should try to be as close as possible to the truth. So the distance that you're away from the exactly correct true assignment, where a true proposition gets a 1 and a false proposition gets a 0, that should be as close as possible to what your credences are. So if your credences are like 60-40, then you're quite a ways up. 70-30, then you're much closer. 80-20, much closer. So, so the idea is that if you have some measure of distance about how far you are from the optimal situation, which is just perfectly true and perfectly false belief, then you can argue that if your credences do not satisfy the axioms of probability theory, then there's an alternative assignment of credences that dominates you, that is better. And since you're aiming at accuracy, the argument is you should be aiming at probabilism, having credences that satisfy the axioms of probability. So the argument for why that is so, and so on and so forth, that I'm not going to go through that. You have to basically prove that for any assignment of credences that isn't in accordance with the axiom of probability theory, there's another one that would dominate you, and so you would be better off having a one that does satisfy the axiom of probability. And so that way of saying that, look, the aim of truth for your beliefs, which we get, at least tentatively through reinforcement learning for truthfulness, the aim of being truthful and accurate gives with it an argument that the rational requirement of having probabilistically coherent credences comes derivatively from that. Okay. So that is the next point, that coherence terms do make sense, not just for logical coherence, but also for probabilistic coherence of credences. These can be justified by thinking about the internal states being properly fine-tuned for truthfulness. But the issue is not quite that simple, I think, because of the thing that I have mentioned earlier. So the thought is simply this. So there is a tension between, on the one hand, the pre-training on inconsistent, incoherent text, and on the other hand, the fine-tuning for truthfulness. Because in some sense here, the model must sort of balance both of those out, and it's not completely clear how it would do that. On the one hand, it should be faithfully learning the training data, which is incoherent text. On the other hand, it should be, faithfully doing what its reinforcement learning is supporting, namely, among other things, being truthful. But how are these two things, how are these two things reconciled? So here's one way to think about it. So suppose, the model's behaving in an overtly inconsistent way. It says this one time and says the opposite the other time. What's really going on? So on the one, you could think that, okay, it is properly responding to the inconsistent, incoherent pre-training training data. Because, the model is trained on the internet is vastly incoherent. What would you expect for a properly functioning machine learning model than to produce incoherent results? You can't blame it for it. You can say it's a failure of rationality if it produces incoherent results in light of the pre-training on incoherent training data. On the other hand, you might think that there's the fine-tuning which should dominate this, that somehow the model should adapt and become coherent or become as much coherent as so that the fine-tuning somehow will override this. Furthermore, there's the thought that maybe, and this might be particularly true for the probabilistic case, maybe in the process of the machine learning itself, it strives for coherence. That somehow the coherence it aims for is a feature of the machine learning process itself. So leaving aside now the fine-tuning for truth, but somehow that the probabilities that get assigned strive to be coherent just by the regular machine learning process. So this is a little bit problematic to pull apart. So is it the case that there is some sort of struggle for coherence, but the struggle gets undermined by incoherent training data? Or is it that there's no struggle for coherence at all and just the model just reflects the incoherent training? So this is hard to determine because all models that we have are trained on inconsistent text. And furthermore, the models need to be large enough to properly learn, say, the meaning of negation and things like that from the text on which they're trained on. So it's very difficult to make sense of what actually is going on in this particular process, in particular when it leads to incoherence. But so there is a way to think of this that might make progress on this particular question. And this is something that with several collaborators that I'll mention in a second, I've been working on part of a team. I mean, obviously, I'm not the team lead on this, but I'm working on this as well. That we can overcome this by doing the following. What you need to do is you would have to have a model that is trained on text that is either not incoherent or is incoherent to a very controllable degree. So you can see that, you have a slight incoherence. It's mostly saying that dim sum is delicious, but a little bit that dim sum is not delicious. And then you see how the probabilities correspond to that. So what you'd have to do is you'd have to train a model from scratch, not using any of the standard pre-trained models that are trained on inconsistent text. Train it on either perfectly consistent or controlled inconsistent text, and then see what the results would be for the relevant assignments of probabilities in this particular case. And the problem for that is you need to have consistent or controlled inconsistent training data that is large enough so you can train a large enough model so that you can actually properly evaluate what it does. And that's, of course, very difficult to do because it's very hard to see for any large body of text, even Wikipedia or something that's reasonably coherent, whether or not it's actually coherent. So the way around this is to just produce the consistent, slightly controlled inconsistent text synthetically. to have synthetic data and then train a model from scratch on the synthetic data to produce and then to evaluate the relevant aspects of rationality. So, so this is basically what we're doing right now. And so, I mean, as I said, I'm not the person on this, so I'm not going to talk about the details of this, but that's a project, I think, to make headway and make an advance in understanding how much rationality is there in these particular language models, how much it is hindered by inconsistent training data, and how much of it simply comes from the fine-tuning for truthfulness. Okay, so overall, though, I think the situation is a little bit unclear. It's a little bit unclear what one should think about all these things, and so let me wrap it up with this particular way. So first, I think belief and credences and rational norms covering them, in particular coherence norms, are on the table, but it's unclear, of course, if ultimately they apply. So there's a question about, are there really representational states? And there's a question about, is there really enough aim of truthfulness in those states such that that you can say this is really a belief state that has as its standard of correctness being truthful, rather than just it contributes slightly. So that's the first worry. Then there's the other worry about the application of the norms of rationality that come from that. So since truthfulness is not the ultimate overreaching goal that you get from the reinforcement learning, this is just one of several things that the model is fine-tuned for, besides helpfulness and besides other things, and of course besides still being the original pre-trained model that is trained on the inconsistent text. So it's not clear if these normative requirements for truthfulness are strong enough to really justify that the norms of rationality, in this simple case, the coherence norms, really do apply. And then furthermore, it's not clear how much of all this carries over to the more complicated cases. So I have only talked about synchronic coherence norms, but then there's also the question about, updating, like, belief revision. How can you make sense of updating in light of new information, and what kind of assignment of probabilities you will get there, and whether or not the logical coherence norms, or even something like Bayesian updating naturally comes from just a machine learning process, if you can make sense of updating a system, and or if it's a requirement that comes externally through some other argument, like the argument for probabilities. Okay, and then just to bring in a benchmark again, so there's the other issue about how would you properly benchmark this? So we don't want to simply benchmark the language models for rationality like we benchmark the trees for politeness. Right? So simply looking at the external behavior, the external features of the system is not good enough, because it doesn't distinguish between the irrational or the irrational or the rational. Simply like benchmarking the trees doesn't distinguish between the apolite, impolite, and polite. The reason why we think that the trees are apolite is because we know about the reason for the placement of the trees in the forest. The trees are not really responsible for being placed in a particular way. They just happen to be like this. There's some other system that outputs the placement of the trees, and the standards of politeness do not apply to this. So the question remains, like, how much of the benchmarking that is done purely externally, including like for reasoning and some of the other fancier things that I didn't talk about, really supports that there are internal states that are subject to rational evaluation, and how much of our judgment of the rationality of the output, the capabilities of like producing coherent reasoning text, is assigned for the internal states being either subject to rational norms and even living up to those rational. So the way to make progress on this, I think, is a little bit tricky. I feel like that one way to make progress is the one that I outlined by trying to build models that are specifically designed for evaluating questions of rationality, and not simply to try to use the pre-existing, already existing in the sense of like the language models that we all have available otherwise, to assess them for rationality, because there is this tension of the inconsistent pre-training data and the reinforcement learning for truthfulness. So, so there is, I think, hope for progress, but my sense is that this whole issue is not really properly resolved, but there is quite a bit to be said for rational norms applying. All right, so oh yeah, here's these collaborators that I'm working with on this, and they're all UNC computer science people, and thank you.